On a very basic level, I've already shown you what a normal EKG tracing looks like. We have a normally round, upright wave that's formed by atrial depolarization, followed by some bigger, sharper waves that correspond with ventricular depolarization, and finally, a rounded wave that corresponds with ventricular repolarization. To be direct about it, those waves are named P, Q, R, S, this bit together is called a QRS complex, and T. That's the convention we've got, and to some extent you'll need to remember that, but hopefully that series shouldn't be too complicated for you. Please reference the alphabet. There's also sometimes an extra deflection following the T wave known as a U wave, which is also connected to ventricular repolarization, but they're not particularly common, so we're going to completely omit those in our discussion until they become relevant. A P wave is, by definition, a deflection on the EKG which corresponds with atrial depolarization. We normally expect this to occur before ventricular depolarization, but when things go wrong, that won't always be the case. Now, a very valid question arises, which is how do I know when something is a P wave? And this will be true for everything else we talk about. You don't. You do not actually know what the deflections you're seeing on an EKG are caused by. You're making strong, educated guesses based on context. And those guesses are strong enough that you can make treatment decisions based on them. But it's important for you to understand that there's always a possibility that what you're seeing is not precisely what you think it is. A P wave can exist by itself. A T wave, or I guess a U wave, which can sometimes look like a P wave, can't, because they're directly tied to ventricular depolarization. So they can't exist without a QRS complex preceding them. So a random displaced wave that looks like it could be a P wave almost certainly is. And this can be one of the signs of AV, or in extreme cases, ventricular dysfunction. The signal isn't causing the ventricles to depolarize for one reason or another. I'm not going to define the exact parameters that make a P wave normal just yet, because those vary by lead, and we haven't defined our leads yet. But, in general, P waves originating from the SA node are upright, that is, positive, and rounded in most leads, and somewhere around a quarter, or sometimes significantly less, of the height of their accompanying QRS complex. Though, it is important to note, as I mentioned just a moment ago, that even though we want them to work together, the two are not directly connected. That is to say, you can have an enlarged P wave without an enlarged QRS complex, or the reverse. The atria and the ventricles are wired together, but they're separate things, and if that wire breaks, they can function separately. A QRS complex altogether visualizes the movement of electricity as the ventricles depolarize. As we've mentioned before, the ventricles are not only significantly larger than the atria, they also contain internal wiring that allows the energy to move faster within them. This makes them tall and sharp. A Q wave is an initial deflection of the QRS complex that is negative. There is only a Q wave, and there won't always be one, if the first movement of the QRS complex is down. So this is a Q wave, this is a Q wave, and neither of these complexes have Q waves. By contrast, an R wave is the first positive deflection of a QRS complex. So, because all of these complexes have positive deflection above the baseline, they all have R waves of varying height. An S wave is the first negative deflection of a QRS complex following an R wave. So, a Q wave only exists if it happens before anything else, an R wave is the first positive deflection, and an S wave only exists after an R wave. One thing to notice here is that whether or not any complex contains all three components, we can still call it a QRS complex when referring to ventricular depolarization as a whole. If we need to talk about more specifics, these complexes can be named as they're shown here, just naming the included waves, and for extra points, capitalizing the biggest one and leaving the rest lowercase. As a quick aside, an actual QRS complex with all three waves is pretty uncommon to find. I dug through my collection and I couldn't really find a good example that actually looks like this. It does happen, it's just not very common. The point here is that this is a theoretical tool for naming the pieces more than a reflection of what the actual distribution of waves looks like most of the time in real people. You'll get used to that pretty quickly, and I'll start introducing more real tracings soon. To review one final time, what we're actually visualizing with a QRS complex is the movement of energy, and when that energy changes direction, we see that manifest as a new wave within the QRS complex. Unfortunately, it can get more than just Q, R, and S. Some pathologies like scar tissue formation from previous damage or problems with the bundle branches can create extra deflections beyond our normal 3. Depending on where you look, the naming conventions for these varies a little bit. Here's an example from one academic article on the topic. We'll dive into this in more depth as it becomes appropriate, but the summary is that additional deflections can be named by adding prime to them. So RS, R prime for this guy here. If you want to call these all fragmented QRS complexes, I won't get upset with you. Finally, the T wave is rounded, nearly always upright in normal situations, and will always follow a QRS complex. A T wave can't exist by itself. These are normally taller than the P wave, but will be shorter than the QRS complex unless there is something wrong. The slope should be more shallow on the upstroke side than on the downstroke side, and changes to the shape of the upslope of the T wave are early indicators of myocardial damage in, for example, the context of ischemia. That definitely gets its own video at some point. So those are the waves. P, Q, R, S, T. And sometimes U.